We're now continuing on, and we're going to look at the hydrogen 1s SALCs in ammonia, which is in C3v symmetry. So we have this here, forming the reducible representation for the 1s's. For your E, your 2 C3s, and your 3 sigma V's. All three stay in the same place. You do a C3 rotation, none stay in the same place. You do one of the mirror planes, one of those atomic orbitals is going to stay in the same place, so that equals 1. And when you reduce this down, this reduces down to the A1 plus the E representation. So we're going to do the projection under A1, the A1 representation on one of those hydrogen 1s orbitals, and we're just going to choose the hydrogen 1s orbital from hydrogen 1. So first, determining where that hydrogen 1s orbital goes under each operation. We have an E, a C3, a C3 squared, a sigma V prime, and a sigma V double prime. E, that 1s stays in the same place. Upon doing the C3, that goes into position 2. Doing the C3 squared goes there. Doing a mirror plane here, it's going to stay in the same place. Doing this reflection here, it's going to go to sigma 3. Doing this reflection here, it's going to go to sigma 2. Okay, totally symmetric representation. Each operation has a character of 1. So sigma 1 plus sigma 2 plus sigma 3 plus sigma 1 plus sigma 3 plus sigma 2. So the projection operator on sigma 1 is going to equal 2 sigma 1 plus 2 sigma 2 plus 2 sigma 3, which is equivalent to sigma 1 plus sigma 2 plus sigma 3. So the wave function for A1 is going to be sigma 1 plus sigma 2 plus sigma 3. And the normalization coefficient is going to be the sum of the square of those coefficients in front of each of those atomic orbitals. So it's going to be 1 over square root of 3. So this is the wave function describing the A1 SALC of the hydrogen 1s orbitals. And I'll just go ahead and draw out what that looks like in the top right-hand corner. So that SALC has all of those 1s orbitals in phase. It's the bonding combination. We're now going to go through and derive the hydrogen 1s SALCs for ammonia, which is in C3v symmetry. If we look at the E representation, we notice that the 3 sigma V's have the character of 0, which is going to simplify the number of operations that we have to do. We only have to consider the E and our 2 C3s. So I'm going to write this out, the transformations on sigma 1 reflecting that. So E, sigma 1, C3, sigma 2, C3 squared, sigma 3. we're going to project that out. Onto sigma 1. So E is 2, C3 is minus 1, and C3 squared is minus 1. So we get 2 sigma 1s minus sigma 2 minus a sigma 3. So when we go through, we get this, and the normalized wave function, 1 over root 6, 2 sigma 1 minus sigma 2 minus sigma 3. That normalization comes from the fact that we have 2 squared plus 1 squared plus 1 squared, so 1 over root 6. As with the E-type SALC under C4v symmetry, in C3v, this E-type SALC has to have another function associated with it, so EA. It turns out that we can't use that simple procedure that we developed by just switching to another one of the atomic orbitals. Turns out that that won't work. So we can't simply project from sigma 2 or sigma 3. So you can go through and do this yourself to find out what happens when you project on sigma 2 and sigma 3. But your wave functions, and I'm going to label these 1. So this would be by projecting on sigma 1. So this would be E from sigma 1. It's 1 over root 6, 2. We get this. Number 2, by doing an E on sigma 2, it's going to be 1 over root 6 minus sigma 1 plus sigma 2 minus sigma 3, and 3 we get these. Now unfortunately, these wave functions here are not orthogonal to one another. And we can go through and determine whether or not these are orthogonal to one another by looking at the sum of the coefficients multiplied together and seeing if these give 0. They give 0, that means that the two wave functions are orthogonal. They give a non-zero value, that means that they're going to be non-orthogonal. So we can look at 1 versus 2. And when we do this, we get 2 times negative 1 for your sigma 1 plus minus 1 times 2 for your sigma 2 plus minus 1 times minus 1 for your sigma 3. And this equals minus 3, which is not equal to 0. So those are not orthogonal wave functions. And for this to be valid, we need to have our wave functions as being orthogonal to one another. What the end result is that we can't simply use sigma 1, sigma 2, or sigma 3 and project out. Instead, we have to use a linear combination of 2 or more of these various wave functions. So I'm going to go through and redo this using a linear combination of sigma 1 and sigma 2. So the two basis functions that we're going to use are going to be sigma 2 plus sigma 3 and sigma 2 minus sigma 3. We could have used sigma 1 and sigma 3 or sigma 1 and sigma 2, and we would have gotten the same result. I'm just going to use these to maintain the orientation of the molecule as I have drawn, and to go comparison back to one of the wave functions that we made, just projecting E onto sigma 1. Okay, so starting with sigma 2 plus sigma 3. We have an E, C2, a C3, and a C3 squared. We don't have to worry about the sigma V's because those go to 0. So E, that linear combination stays the same. You do a C3 rotation, sigma 3 goes to sigma 1. So that goes there. Sigma 2 goes to sigma 3. So this would be sigma 1 plus sigma 3. You do that C3 squared. Sigma 2 goes all the way to sigma 1. Sigma 3 goes all the way to sigma 2. So this comes out as sigma 1 plus sigma 2. Projecting through, E goes as 2, C3 is minus 1, C3 squared has minus 1. You get 2 sigma 2, 2 sigma 3, minus sigma 1, minus sigma 3, minus sigma 1, minus sigma 2. The overall E from projecting out is going to be negative 2 sigma 1 plus sigma 2 plus sigma 3. So the wave function for that first pair is going to be 1 over root 6 negative 2 sigma 1 plus sigma 2 plus sigma 3. So this looks very similar to the one that we derived just projecting on 1. It's just that the signs of our coefficients have changed, which will come out in the wash when you actually go through and construct molecular orbital diagrams using this wave function here. Where the change really comes, though, is when we project on the out of phase combination, the sigma 2 minus the sigma 3. Going through and doing the same procedure for sigma 2 minus sigma 3, we get a sigma 2 minus sigma 3. We go through and we get a negative sigma 1 plus a sigma 3. The positive sigma 2 goes to sigma 3. The negative sigma 3 goes to sigma 1. And we get a positive sigma 1 minus sigma 2. The positive sigma 2 goes through to sigma 1, and the negative sigma 3 goes through to sigma 2. Projecting E onto there. Have a 2. C3 has a character of minus 1. C3 squared is also minus 1. So you get 2 sigma 2 minus 2 sigma 3 plus sigma 1 minus sigma 3 minus sigma 1 plus sigma 2 So what this simplifies down to is 3 sigma 2 minus 3 sigma 3 sigma 2 minus sigma 3. So the wave function for the B component, 1 over root 2 sigma 2 minus sigma 3. And we can go through and show that this is orthogonal to the prior wave function. Just to remind you, we can go through, multiply -2 times 0 plus 1 times 1 plus 1 times -1 equals 0. So EA and EB are orthogonal to one another, so these are valid wave functions for the hydrogen 1s SALCs under C3v symmetry. So going through and briefly summarizing our results, the A1 SALC represents our in-phase combinations of our 1s orbitals. Looks like this. So it's going to overlap with A1 type atomic orbitals. So your S, the PZ, and the DZ squared. Then you have your two E-SALCs, which are these. So your EA, large contribution that's out of phase on the 1s, 2 and 3 are in phase. And then this is your EB. This EA SALC will overlap with, if we draw our molecular axes such that the X is oriented here and the Y is oriented here, your EA will overlap with PY, DYZ, and dx squared minus y squared, if you have available d orbitals that can bind in. The degenerate p type combination will come from px, and the degenerate d combinations will be the dxz and the dxy. Like that. We're now going to generate SALCs for the px orbitals under C3v symmetry. So first we need to form the reducible representation for the pi type orbitals. E 2C3, 3 sigma v. E, all three stay in the same place. C3, none stay in the same place. For the sigma v, we get a -1. And this is because as you do this mirror plane reflection, this transforms into this with 1, 3, and 2. When you reduce this down, the reducible representation forms an A2 and it contains the E representation. So what we're going to do is we're just going to see how pi1 transforms upon doing an E, a C3, a C3 squared, sigma V prime, sigma V double prime. So E stays in the same place. C3, it goes into pi 2. C3 squared goes into pi 3. Sigma V, negative pi 1. Sigma V prime goes into negative pi 3. and sigma v double prime negative pi 2. We're now going to go through and project out the SALC using the pi 1 atomic orbital. E has a 1, C3 has a character of a 1, C3 squared, character of a 1, sigma v for the A2 rep has a character of a -1, sigma v prime -1, sigma v double prime -1. So we have pi 1 plus pi 2 plus pi 3 plus pi 1 plus pi 3 plus pi 2. So the projection operator on pi 1 yields 2 pi 1 plus 2 pi 2 plus 2 pi 3. Reducing that, pi 1 plus pi 2 plus pi 3. So the wave function, after we normalize it with the 1 over root 3 coefficient, will be pi 1 plus pi 2 plus pi 3. And it's going to look like we have depicted up here. So this is what the SALC for the A2 set of orbitals look like in the for px orbitals. We're now going to derive the degenerate wave functions for the E-SALCs. And just as we generated a linear combination of pi-type orbitals before, we're going to do that again. So we're going to use here pi 2 plus pi 3 and pi 2 minus pi 3 as our linear combinations. We can ignore the sigma v's because those have characters of 0 under this point group. So we're just going to look to see how pi 2 plus pi 3 transforms with E, C3, C3 squared, pi 2 minus pi 3 goes with E, C3, and C3 squared. So we get a pi 2 plus pi 3, we get a pi 1 plus pi 3, and a pi 1 plus pi 2. For pi 2 minus pi 3, E, we have pi 2 minus pi 3. The C3 rotation brings pi 2 into pi 3 and minus pi 3 to minus pi 1. So we have minus pi 1 plus pi 3. And then the C3 squared, we have pi 1 because pi 2 comes over to pi 1. And then the minus pi 2 because minus pi 3 goes to pi 2. We're now going to project out our SALCs on these two basis functions. Starting with the in-phase function, E has a character of 2, C3 minus 1, C3 squared minus 1. So we have 2 pi 2 plus pi 3 minus pi 1 minus pi 3 minus pi 1 minus pi 2. The projection thus yields negative 2 pi 1 plus pi pi2 plus pi3. So EA 1 over root 6 minus 2 pi1 plus pi2 plus pi3. We're now going to go through and project out the other SALC using the out-of-phase basis function. So we have 2 pi2 minus 2 pi3 plus pi1 minus pi3 minus pi1 plus pi2. This therefore yields 3 pi2 minus 3 pi3, which reduces to pi2 minus pi3. So the other wave function of E symmetry is 1 over root 2 pi2 minus pi3. So now going through and drawing what these look like, I'm going to reorient the molecule a little bit. So for the A1, that equals 1 over root 3 pi1 plus pi2 plus pi3. So this is the higher energy SALC because it has several nodes in it. We have a node going here, we have a node going here, and we have a node going here. Okay. So this is going to be the highest energy SALC. The EA and EB degenerate wave functions are going to be lower in energy because they have fewer nodes associated with them. So one of them, 1 over root 6, 2 pi1, pi2, plus pi3. So what this looks like, we have pi1 large, and it's changed, it's inverted where the phase is. Then we have this, and we have this. So this has one node, it's right down the middle there, and the EB wave function is this. So it looks like that, and this has a node going this way. For the Pi-SALCs, which come in and out of the screen, you can go through and see that the Pi-SALCs under C3v symmetry transform in the same way that the S-SALCs transform. So they transform as an A1 plus an E. The overall signs are going to be the same for those, and you can go through and work out what these look like. In the next video, we're going to be using these SALCs to generate more complex MO diagrams than we've generated before.